Welcome to the Q-munity Tutor TipVid section 1 on the mysteries of quantum physics. And I think you're going to find this quite amazing. Now, today I'm going to talk about, the tip is about the delayed choice quantum eraser experiment. What upsets me is that this is an absolutely unbelievable experiment. It's only 20 years old. And it looks so much more complex and complicated than it actually is. So the point of this TipVid is to basically break it down so it's very easy to understand. Okay, as I say, it looks far more complicated. I'm going to break it down. There are 2 points that it makes, basically. One, that you don't have to make a direct observation or measurement to collapse the wave function. You'll find many scientists object to the double slit because they say when you have the camera there trying to measure it, the light from the camera which does measuring affects the subatomic particle, and there's a fair lot of logic in that. But this one here, this experiment shows that just by using your intellect or just by inferring where the photon or electron has gone through, it is enough to collapse the wave function. It also shows a very strange effect because basically it's the double slit, but with entangled particles. And it shows that entangled particles operate over time, temporal quantum entanglements, as well as distance. And in effect, it shows that events that have already happened can be altered. And I know that sounds weird, but that's the way it is. I just want to mention the equipment because that throws people off. And you've got the BBO crystal, all that does is entangle the two particles. You've got lenses, which focuses the photons, it redirects them to the detectors. Now, the thing that is important is the beam splitters, because what they do is 50% of the time, and we don't know when, it's completely random, 50% of the time the photon goes through, and 50% of the time, the photon is reflected by the beam splitter. So that's that's obfuscating the path of the photon. The prism just redirects the photon so that we can study it better. And then very importantly, the coincidence counter. And this is really key because the coincidence counter is the equipment that basically lets us analyze the results. So that's got to be exact. Okay, well, look, here we have the photon coming in, and then we have the traditional double slit. And immediately after the photons come in, we have a BBO crystal, which entangles the particles. All you need to know that it's entangled. One of the entangled particles then goes to the first detector, D0. Now, its entangled brother, what I should say is that this takes 1 unit of time. It can be an absolute nanosecond. This other one here, its entangled brother, partner, sister, goes through a web of beam splitters and mirrors, and basically it completely obfuscates the path that photon takes. And there's only 2 results. One, we know the which way, which is just the path. and then another detector where we don't know the which way. Now, you see, the which way is the important thing. This is Heisenberg's uncertainty principle. We're not allowed to know the path, the momentum, and the location of the photon. So we're not allowed to know how it traveled and the way it traveled. And nature seems to be stopping us. So that's basically the setup. Now, the amazing thing is this. Oh, and what I should have said, sorry, is that to get to this second, to both of these second detectors takes 2 units of time, because it's got to go through all these mirrors and all these beam splitters. But we know that entangled particles must show the same pattern, i.e. interference or clump. You know, if one of them's a wave, the other one must be a wave. If one of them's a particle, the other one must be a particle. So they have this wonderful bond, but the first one that gets up here, Johnny, that gets to the first one, always displays the same pattern, be it interference or clump, as the one that whichever it gets and the second one goes to. Bear in mind, by the time the first one gets to its detector, it doesn't know how the particle, its entangled particle, is going to go through this maze of mirrors and beam splitters. Yet, believe it or not, the patterns are always the same. And that's measured by the coincidence counter. So that is amazing when you think about it. It's like the second particle updates the first entangled particle. So it says, look, I came to the mirrors and we know the which way. Therefore, because we know the path, it's going to be a clump. Therefore, you have to be a clump. No matter what you were, you're now a clump. And that's pretty amazing. I might just take it one step further, because you see, using the same delayed choice concept, one of the most intelligent people who's ever lived, John Wheeler, Professor John Wheeler and Professor John von Neumann, they said, what if there's a star, Andromeda spiral, our nearest galaxy, and a particle of light is sent from Andromeda spiral, and we know that light bends with gravity. Einstein proved this many, many times, many, many years ago, with a very famous experiment where they all went to the Seychelles or something, and Einstein said the star behind the sun will be here, and Newtonian law said it would be here, and Einstein was right. Now, let's just say we've got a huge cloud of, it could be dark matter, or it could be baryonic matter, it could be real matter, if you like. Doesn't matter. Oh, I didn't mean that. Now, the photon will make a choice, well, it won't make a choice, but it will actually go one way or the other, and then, you know, come back to the Earth. So we've got the Earth here. Now, believe it or not, when we get here, we've got a choice to measure it through a telescope, and we will know the which way. Or we could measure it through what's called an interferometer, which is the equipment that detected, which is very accurate equipment, it detected the gravitational waves. But if we measure that way, we don't know the which way. So this would be a clump. This would be a wave. This means the photon has traveled as a particle of light. This means it's traveled as a wave. I should have said clump and interference. So what we're saying, and this is what we call a Gedanken. So it's a thought experiment. So we're saying, or John Wheeler and John von Neumann, and you don't disagree with those guys straight away without thinking about it, but they were saying, depending on how we measure that light now, will change the path it's taken, which could be 1 billion years. So for 1 billion years, it traveled, if you like, as a particle. But if we look at it through an interferometer, it will somehow it will be a wave and will have always been a wave. So the past is being rewritten, at least in the quantum realm. Thank you very much. I hope this tip has helped you understand one of the greatest experiments there'll possibly ever be, the delayed choice quantum eraser. And I'll catch you in the next session. Thank you.